Hi again. So, welcome to today's class. The agenda for today is quite simple. After a very brief recapitulation of what we talked about yesterday, I will, my ambition is to describe two new algorithms in the public key cryptography domain, which are of um, large importance in different security applications. But before I start, maybe I can ask you if you have any questions based on what we learned yesterday. Let's see. Well, if you have questions, please ask in the chat at any time. And today I will heavily use pen and paper presentation. So I will upload PDF obviously with my handwritten notes after the class to Canvas. I want to start with the question. So we finished yesterday about PIN and how it is used in the context of credit card. But let me ask you. So did you? Yeah, I will do some repetition, obviously. So we will do it. So, but I mean, let's start with somewhat simpler topic. There was a question, I think Ian asked it about how, I mean, what is the role of PIN and how it is used in the uh, cryptographic cryptographic protection of bank transactions. So did you do any own research on the topic? So can you tell us? Anyone can tell us what it is used for and how? Let's see. Um, well, let's then start with this figure in the yesterday's presentation about how authentication happens. And so the authentication when using credit card happens using certificate signed with the public key uh, mm, uh, or with a certificate of card's public key and which is signed by the issuer, so by the issuer of the card, so the bank. And but then the question was, so how PIN is used for in the context of these transactions. So PIN is used in the first place by the bank itself. So it is communicated all the way to the bank to so that the bank can confirm that you are the owner of the card. And PIN is encoded using symmetric key crypto algorithm like DES or AES. I think most of the banks use DES, Digital Encryption Standard, for these purposes. And the keys are pre-recorded, and kind of exchanged between the terminals supporting the system. So as payment system of the particular card. So it is used for first level authentication. So you authenticate yourself to the bank that you is the owner of the card. So the certificate, so the public key cryptography is used for local authentication of you to a terminal. And actually, so this signing procedure uh, is used by the terminal to be sure that you have the right encryption key. So your public key um, can be used to verify the signature, and uh, uh, so that you can so that the terminal can also send you the transaction and you can sign it because you have your private key. And by signing it, so later on, well, maybe not immediately, so the terminal or the bank of this terminal can send this transaction and claim the money from your home bank. Yes, let's maybe very quickly repeat what we learned yesterday so that we are on the same page. And the repetition will concern this algorithm. So we are, um, well, we have considered an instance of asymmetric cryptography algorithm. So asymmetric means that you encrypt with one key material and decrypt with another key material. So this equation over here, so I just highlighted. So this is this equation describes the encryption procedure. So you have the plain text and you transform it into ciphertext. And for this operation, you need two numbers, the modulus and the exponent, e. To decrypt the message, you use, well, exactly the same operation, but using different numbers. So we use same modulus and different exponent. So the whole strength of this algorithm is in the choice of these three numbers. So they are very tightly interrelated between each other. Okay. And the way how they related is described here. So you generate n as a product, as a multiplication of two large prime numbers. And then you use this, then you use these two numbers also to compute a special number, which is called totient function, which counts the number of relatively prime numbers with P and Q correspondingly. So since they are primes, then so all numbers but one, so until P, will be relatively prime, so to P. And the same is valid for Q. So and it means that so number of relatively prime numbers to P will be 1 minus P minus 1, and number of relatively prime numbers to Q will be Q minus 1. So for the product of these two, it's simply a product of these two values, P minus 1 and Q minus 1. And in this way, we compute phi n. And later on, this number is used for generation of E and D, so this exponents. So this E and D, they're related to phi of n over here. And here we come to the first strength of the algorithm. So later on, so you will use combination E n as a public key and dn as a private key. So what's the catch? The catch is uh, if you know E and N, it should be computationally infeasible. So it's very, very complex and, well, 99.99999% impossible to find D. And why is it impossible? Well, because of a simple thing. So for generating E and D, you need to know this value. And to compute this value, you need to know P and Q. And these numbers, this number and P and Q, you never reveal to the outside. So it's not that you keep them in secret, you simply forget them. And as well as you forget phi of n after the generation. So you only use n, e, and d for your computations, right? So this is the first strength of the algorithm. So knowing this n, and remember, p and q are very large prime numbers, so it's very hard to generate prime numbers. But it's even harder. So it is called large number factorization problem. So knowing n to find which of the p and q was used to produce it. And without knowing p and q, you cannot generate this phi of n. And without phi of n, you cannot deduce d knowing e. So you see, this is the first strength of the algorithm. So a strength with respect to breaking the key. It's not so now. The question in the chat: what kind of operation is EM? It's not an operation. It's a pair of numbers. So I can refer to this very first slide. So remember, I showed you a certificate of this website. And if you go into details of the certificate and you select the public key algorithm and the public key itself, then you will see two numbers. So modulus and an exponent. Modulus exponent. So, and this notation here, well, n is the modulus. So let me n n is the modulus and e is exponent. All right, and d is the exponent of the private key. So, okay. So, and that's what I mean. Your understanding should be. So, at least. So that's for encrypting certain message M. And M in this case should be converted to a number. You take this M, the message, so this number, raise it to the power E, and take a modulus. So this is the encryption. And again, so if you do it in this way, so using somebody's else public exponent, so you do encryption to achieve confidentiality. So only the one who knows D, so the private part, will be able to decrypt it. So it will take this C, do the same operation, raise it to the power of private exponent, take the modulus n. N is always public, as you see it here. And it will compute M. So I will not trace again the computation. So we demonstrated it yesterday that it holds true. Yeah, well, it comes automatically here. Okay, so that's it. And here is the strength of the encryption itself. So it is hidden in this very operation. So you raise it to the power and take a modulus. So the encryption itself is another hard to compute problem. So it means that knowing C and knowing N, you cannot take inverse of this. And remember, yesterday we considered a couple of cases where it is possible. So basically, um, uh, when this number is very, very small, and exponent is also very small because I mean this exponent can be chosen small for speed of computation, then this module doesn't work simply. And then you can take ETH root to compute the message. So that's in this case is not an encryption. But given larger result of this operation larger than n, then it works. So then it's computationally hard problem. So you cannot inverse it directly. Okay, I hope this recapitulation helps. So do you have any more clarification questions? But I mean, this is, as I said, the bare minimum of what you have to understand. I mean, I will not ask you to, for example, trace this proof that I mean you actually do, but I mean just understand that it works. And then next week you will work with this public RSA algorithm to actually try encrypting, decrypting, I mean, writing a program for that, and also for using your program to manually decrypt certificates. So that's what we have been talking, considering these use cases, different use cases for authentication of a web page to a bank and cards authentication. And yeah, another important moment to remember is that one of the downsides of the public key algorithms, cryptographic algorithms, is still high complexity, high computational complexity, because you need to rise something to the power, and that's very time consuming. So and that is why public key crypto is normally used to encrypt smaller portions of text. So as in this case, for example, you encrypt a key for which can be used for further encryption, or you can well, you encrypt a digest of a message that you computed using a secure hash function that we considered some weeks ago. Okay, so let's move on. Let's move on to the new material. So let's see here. Yes. Let us talk about a new algorithm, which actually came about first before RSA, and it was proposed by two people, Diffie and Hellman. And so the idea was to create an algorithm that allow communication of a secret information over a shared channel. So you want to share a secret while everybody is listening to your conversation. So how to do that? And for this purpose, maybe I can switch directly to this diagram over here. So you need to agree upon two numbers. So large numbers, p and being prime number, large in the order of uh, more than 2000 bits. So it's a huge number. And also G, which is called a generator. So you will see it now how it works. And so again, so very similarly to encryption to encryption equation for RSA. So Diffie and Hellman, so they proposed to use this operation to share a secret. So how is it working? So actually very simple. So you generate a random number, x, and you raise g to the power of x. So this number should be large as well. And you send this quantity over to Bob. And again, so the catch here is that knowing this result, so I mean, here it is written as a mathematical equation or a formula. What you send actually is the result of computation, a number, a large 2048-bit number. And the catch is here that knowing G, knowing P, and knowing the result of the computation, it is computationally impossible. It's mathematically proven that it is computationally very hard or impossible to compute X. So then, yes. So are you with me here? So let me check. So basically, knowing the number, so the result of this computation, knowing G and P as publicly available parameters, so you send it over insecure channel, you cannot compute X. Okay, how it helps our Bob, so the one with whom we want to share the secret, to use it? Well, actually, in a pretty much similar way. Bob also generates a random number, y. It keeps it secret and computes the same formula, so and sends the result of computation to Alice. So now both of them uh, have uh, have these numbers. Uh, um, so they exchange these numbers. So to compute the shared key, then so what you actually do, so Alice takes the number that she got from Bob and writes it to the power of X. Remember, she knows the X because she has it. So, she keeps it in secret. Nobody else know it. So they know only the results of the computations. And then and Bob does the same. So it takes Alice number and raises it to the power of y that it keeps locally. And the result is mathematically the result of this operation will be equal. So and these number will be used as the shared secret. So this is pretty much simple uh, math. So it's I mean the mathematical properties of rising to the power and modular taking modular is written here in this line. So And what you can do with it now, so you can use this key, for example, to create, I mean, to derive a key for symmetric key crypto and encrypt it fast. However, you can also use this technique in the public key manner. So what you do in this case is shown on this diagram. So you again, so you I mean Alice as the first actor in this communication session. So she creates X as before, and together with G and P, so well, which are publicly known, um, these three numbers corresponds to a private key. And the public key will be decomputed according to this formula number, which she can publish on the web page, for example. So what Bob does to encrypt a message using public key principles, so it generates own number, secret number, and computes and computes as previously. So it rises to the power the result of Alice computation. So Alice's public key, right? And so this value is now used to encrypt a message. So what you communicate the crypto text and the portion and the number which will help Alice to find the to compute the key. So the key computation, as you see here and here, is the same. So it's just two different modes of operation. So uh, you can think of it as a public key style encryption. Let me see. Does they create a key in this way? No, it's I mean VPN rather uses. Well, no, they don't use Diffie-Hellman directly. VPN's scheme is very similar to. Let me show you to. Uh, where is it? Um, to this operation. So in VPN, the keys are they can be renewed using this technique. So you encode it using public key, and then communicate it to the other end, and then you use this key to um, you use this key in the context of symmetric key encryption. But again, what is used in the context of VPN or secure socket layer SSL, which is behind HTTPS. So it is all decided during the negotiation phase, so during the connection establishment, where client and the server agree on the exact protocols which will be used for different purposes, for exchange of initial key, for update of key materials, etc. So, and normally there are several options available for the server and the client. So maybe while we are still here, let me see if I can quickly go here. I want you now to look at this protocol of key exchange. and think whether think about a possible attack to this protocol. So, what kind of attack is still applicable um, to this key exchange scheme? So, I give you one minute.
Maybe step one.
In step one, well, step one here is well, it should be here. So, I mean, it should be publicly. You need to communicate it publicly. So that I mean, you cannot avoid step one. Maybe I can sketch the following uh, scenario. So then you will see what I mean. So if we have our Alice, so Alice, and here we have our intruder and a Bob. So this scheme is susceptible to so-called man-in-the-middle attack. I mean, as many other schemes, and that's why I mean, people. I mean, you cannot avoid authentication, constant authentication. You need to be sure that you're talking to a right partner. And Richard log jam attacks. Uh, can you send a link? Or yes, but Max, at least this is the attack I want to talk about. But Richard, I'm intrigued. Maybe uh, I can miss something. Logjam. Okay, I will read it in the during the break. So, but the man in the middle here is very straightforward. So, when Alice sends its G, so it creates a secret X, and this one it creates secret Y, and this guy in the middle it can create secret Z. So, when Alice sends its G to the power of X mod P. So over here, so this request can be intercepted. How it is intercepted? So this is a different business. So it can be, for example, a fake website that you believe you are talking to Bob, but because it looks like Bob, but indeed it's somebody else. And so you basically so this intruder, so it sends its own challenge, GX mode P to Bob. Then. And here it answers obviously to back to Alice, saying, okay, now it was your GX mode P, and I raised it to the power of Z. Yes. And the same goes here. So this one just replies. Oh, sorry, here I was not very accurate. G to the power of Z. So I took your G to the power of Z, P, and I raised it to the power of Y. So now, basically, the man-in-the-middle attack is performed. So you establish two channels to Alice and to Bob, and can intercept all the communication. So let me just clarify, man in the middle. And I check in the during the break this link. Yes. Okay, but maybe and that is it about Diffie-Hellman. What I wanted to say. Uh, Now we will take a short break for 5 minutes, and then we will talk about yet another algorithm. So one of the problems still with Diffie-Hellman and um, RSA is this exponentiation over here. So uh, engineers, well, security engineers and researchers were thinking if they can come up with a scheme with similar properties, but which is not relying on this exponentiation. And that's what we will be talking about after the break. So we will talk about elliptic curve cryptography. So let's have 5 minutes break. So we return here by quarter to 9. So let me pause the recording. Um, yeah, just a quick comment. Indeed, logjam is one of the possible attacks. It also belongs to the, general class of man in the middle. So you have this log jam. So you have Alice, but now Bob doesn't. Alice and Bob, so they are participating in the exchange. So first G and P, and then G to the power of X log. No, sorry, but I'm saying mod P and back. So G to power X mod P to the power of Y. So these three steps. So now our intruder is able to record all three messages. So this three messages. And for some values or for some special cases when this P is about 1000 bit or 1024 to be the exact bit long, and all other basically numbers are of this kind. So then, there is an algorithm uh, which can be computed efficiently in a matter of minutes that can compute the X. So knowing all these numbers. And this is based on mathematical properties of fields. Field is a construct, is an algebraic construct. We will be talking about fields again very, very shortly in the context of elliptic curve cryptography. But again, so this attack is rather complicated to describe because it's really based on the math of fields. But the recommendation is that this attack becomes more complex for larger sizes of parameters involved in the Diffie-Hellman exchange. So, for example, 2048 bit numbers. Yes. So let us switch to the next topic, which is elliptic curve cryptography. Well, there is quite some math involved in these algorithms as well. So uh, to show the proof that the system works, you cannot escape doing some math. So what I will show you is again the bare minimum, so not to allow the main operations of this algorithm. So without going deep into details. And again, I will focus on computational efficiency of this scheme. So the general idea, first, let us digest this title over here. So, well, cryptography means that we will encrypt somehow something, and uh, or at least we will derive keys for that purpose. So either to encrypt for confidentiality purposes or for signature. So I will, in particular, I will demonstrate the digital signature part. And the first part of the title tells us that it will be used something which is called an elliptic curve. So elliptic curve, so I will show you a more precise drawing of it, but you can view it as this kind of trajectory. So it's a curve, and a curve with a specific shape of this kind. So you see, it's kind of symmetric, and so this would be our y, and that would be our x axis. And the main principle for what I will show you later uh, is doing all computations on values which reside on this trajectory somehow. So so use only values of the curve. So, I mean, for example, this value is invalid. I mean, for XY combination. Um, X. So this is totally invalid. So this is invalid. So this is valid. This is valid. So we want that all our results somehow be on this curve. And now I will show you again this math that actually will help us to do this. And moreover, so again, on a very high level, uh, so this is the first principle, so that we want uh, uh, to delimit our range of values for pairs x and y to this curve. And secondly, so all computations uh, will be done on transformation of coordinates. Using simple, computationally simple. Simple uh, uh, transformation of x and y. And here is not valid point for this one as well. And here are valid points. So we need kind of mathematical apparatus that allows us to do this kind of computation. So these are valid points over here. So far, so good, right? So now we need to introduce mathematical notation somehow. And so, and again, so there are different forms to characterize this trajectory over here. So the simplest form would be of the following kind. So y square uh, equals x cube plus ax plus b. So this is our equation. Y square x cube ax plus b. And already again, so maybe if you recall even school math, so this y square is responsible for the symmetry of so I mean you remember a parabola equation for parabola, so it's a square equation, but this x cube is responsible for these kind of shapes. So and as you see, so it will be a combination of some symmetric behavior and this kind of functions. I want to show you some more examples now using a special tool for mathematical computation. So let me just find it where it is here. Well, this is something, again, just for demonstration purposes, just to show you that, I mean, it works. So you will never use it for labs again. So this is just for visual demonstration. So what is shown here is, for example, this is another elliptic curve. So compare it to what we've seen here. So we added, let me just, so you see it has a slightly different form. So we have y not only squared but also y, and also so we don't have this. So a is 1, b is 0, so like this. And if you plot it, actually, so if you run it, then you will have a I mean, you will see a picture like this. So that's kind of this is one type of elliptic curve. I mean, a valid type of elliptic curve. Uh, but that, for example, if we take this equation over here, but maybe I will simplify it a little bit by saying that this a equals to 0, so we have only y square uh, x cube plus b, and let's b equals to 7. So then you will see a similar shape as I have drawn here. So if you will visualize it. Okay. Uh, Next step, what you can do, again, using this, um, using math, you can say, well, we want to limit, we want to introduce another limit. So so in addition to this limit, to this requirement number one, that all valid points should be located on this curve. So let's enumerate them. Uh, we have another requirement, 3. So that's uh, all these points on the curve, all values of our computations are integers. And less than some p. And now this p can be in principle large. Well, not in principle. I mean, even actually it is large, and you use it. You choose it as being prime. Uh, what does this third requirement tells us, or how to approach implementing it? That's kind of easy. So you take modulus. So you take modulus. So let me just make another page. So implementing 3. So you have y square equals to x cubed plus ax plus b. And if you want to implement 3, you do the following. So you say y square mod p, and this equals to this whole thing, x cubed plus ax plus b mod p. Right? So what you achieve here, so all your numbers, all results of computations, they will be always within the range between 0 and p. So this is the property of modulus, right? Moreover, the modulus of the property of modulo operation is it's a reminder, integer reminder of the division. So it's always integer. So here I have another demonstration, just for you not only to believe me, but to demonstrate that this is the case. So it's the same equation of this form, now implementing modulus. So modulus and base 17. So P is 17 now. And let's see what is going on here. So if you visualize it, you will see a picture like this. So these are discrete points. You see there is some symmetry, and all numbers of this curve, original curve, are now integers in the interval 0 to 17. Well, it never goes to 17, but like this. Okay? And now we are coming to a very interesting thing. So what does it mean that we want to remain so that our results always um, reside on this curve. It means that we can choose a point. So, well, for now, I mean, we don't say any requirement, but you choose a point. So let me just maybe somehow reproduce this thing here. So now we have only positive values. So and again, I will just sketch. So I will not do exact. Mhm. Good. And symmetrically here. So something like that. So good enough. X and Y over here. So these are our valid points. So these are our valid points uh, of, uh, of this curve. And now we choose uh, one of them. So what does it mean choose? You choose X and Y coordinate for these points. So numbers, so integers. So say X. Let's denote it as X G large G and Y large G. So that is this point over here. So let's call it G. And now, so we need some simple rules to start counting. So you add, so you want to derive all other points starting from from this point G. Um, a similar analogy, I mean, you can find in our, usual arithmetics. So if you take all the integers, right? If you take all the integers from say from 1 to 10, so let's limit our range from 1 to 10, and take and say and you want to create a rule to derive all integers in this range starting from 1. So how you would do that? You would add 1, right? So you would add 1 to 1, you get 2. You add 1 to 2, you get 3. You add 1 to 3. So it's simple, so right? But this is a rule on how you can generate all the valid points in a given range, right? And by the way, again, so the long story short, mathematically, if you have this range of numbers, so finite range of numbers, and an operation, and you define a special point and an operation that allows to generate all other points from this range. So this construct, this mathematical construct, is called a field. So it was I mentioned this word when talking about logjam attacks. So field is nothing more than a range of numbers. In addition, you need to define one of these numbers as a special number and an operation to derive all other points, all other numbers. So in this case, you are talking a field. So the same thing is here. So you define the number, so a valid point on the curve, and now I will just skip the long math and just show you examples of these derivations. So you can derive all other points on the curve by simple by applying all same operations to subsequent points. But in this case, in the case of elliptic curve, I mean, this you cannot use the same intuition as with in this example I gave before for the range 1 to 10. So, for example, the next point from this one can, for example, be uh, this point. From this point, if you apply the same operation, you can jump maybe here, then you can jump over here. But nevertheless, so I mean, when applying this number, so eventually, so you will visit all the points that are displayed here. And importantly to us, to know that this point G is called a generator rator of field field. And uh, we are talking about field. Uh, so a field is characterized by this range number. So it's field P. So it's a finite field P. All right. And now I only, again, I will skip this the actual derivation of these rules. I can just show you um, uh, sample equations or example of uh, formulas to derive new points, uh, new points on a curve. And let me see. So, for example, if you want, so if you have 4 point, uh, let how to call it, say G. So for a point G, or let's use a small letter G. So let's uh, let's define coordinate transformation, which corresponding to uh, operation G plus G. So you take one point and you want to add you want to add itself, and you still want to. So if you take this point, so you are interested, what would be the point which corresponds to addition of this point to itself? So, or in other words, it's like 2G. So if you double the point. I mean, again, in normal arithmetics, so in our in that algebra that we know, so you take two, so number, I mean, doubling two equals four, right? So that's here it's the same principle, but so what is would be the equivalent of saying taking point 2, 10 and doubling it. So it should result in one of these valid points over here. And again, so I just want to show you the final result of it. So so your point X, let's put it, so the coordinate. So now we talk, this is coordinate X of 2G. So X of 2G point would be computed as the following. So I just list this equation. Lambda square minus 2x g. So that you know. So this is the x coordinate. And y coordinate of 2g point would be, again, lambda x g minus x 2g. So that one we have just computed, minus y of the original point. And lambda would be 3x g squared plus a divided by 2yg. So this a is a parameter of our curve. So y square equals x cubed plus a x plus b. So this is a here and a here. So the long story short, so I will not torture you with a kind of math on how to actually derive these equations. What is important? So now what I showed you transformation. So if you are given some coordinates x and y, and you will be given it by I will show you where, or I can show you already now. So if we would go to again to the very first slides, this one. Oh, sorry. So let me just bring it up and enlarge it. Bring the front. So that will be part of your specification of the algorithm. So you will be given an equation and you will be given numbers. You will be given numbers for A, for B, for the range P of your field. So that's all these numbers you will be given, and you will be given coordinates for this node G, which is I mean for the point G. And here, if you see, so it's a huge number, so it's in a hexadecimal format. So for X coordinate, comma, Y coordinate. So you know this, uh, you know that X, G and Y, G. So it means that to derive new points, so you will apply some, computationally simple operation. So you see there is no exponentiation. So it's like squaring of some values and multiplication, summation, and subtraction. So that's this transformation is simple. Okay. And now I will sketch you um, how to create a security scheme based on this elliptic curve cryptography. Again, what you need to understand from this, of course, I mean, I mean, it's not the mathematical details of all that, but the general principle of the stuff. So, but before all, I want to probably return to this figure over here and say what would be the security principle. So first of all, so we will use this elliptic curve construct, this one, uh, and which will be specified by parameters a, b, p, and this g. We will use it to compute a secret. And how we use, I mean, to do this, we will use a very simple intuition. So we want to start with this G, so that's given to us, and so we will choose a random number K. So let me just how to security principle. Choose random K, and keep it in secret. So this will be your private part, so secret. And uh, what you do for a public part, public key, so something that you will expose uh, to all the rest key will be K times G. So you will do K iterations, so adding G to itself. So here I traced transformation of coordinates when adding G to itself one time, so 2G. So there are similar equations when you want when you would. So let me just write a note about it. So similar equations or formulas they exist for computing the following. For example, 2G plus G, which is 3G, right? And in the same fashion, so if you want to, for example, 4G, you first uh, compute. So you basically add to the result of 3G to the point another G. And in this case, in this manner, so you would do K iterations. So to compute public key, uh, you do key K iterations of summation starting from G, which is given to you by the specification over here. Okay. So now I will conclude the picture uh, just very briefly sketching 5 steps for creating a signature. So an algorithm which is called elliptic curve digital signature. Digital signature algorithm. So digital signature. So this algorithm, for example, is used well to verify some certificates. So, for example, ChatGPT uses yeah, or certificate of ChatGPT relies on this algorithm, uh, as well as let me see. For example, this is the default signature scheme in Bitcoin currency and similar. So in cryptocurrency. So yeah, and again, why it is used? Because of this simple operation. So for efficient execution. So because of absence of this exponentiation. So what you start with. So you want to sign message M. So what you do for that? So next, you create hash hash. So say SHA to 256 or something, a hash of M, and let's denote it as H. So far it's understandable, right? So you create a hash of message, so no big deal. Um, so you generate key. So generate uh, this K, or you can normally this K that will be used. So you can again use HMAC scheme. So a hash based scheme for um, the original hash and K private. So you basically create a kind of signed hash. So with your private key involved. But again, so that's maybe not very important. So somehow you generate a key based on certain rule, and then you calculate this random point on the curve. Calculate a random point on curve, which is R equals K multiplied by G. So, and what you do basically, you take X coordinate of it. So take X coordinate of it. So let's denote it as R equals R dot X. So R is an integer, so it's X coordinate of the point that you generated in this fashion. And so you calculate signature. Signature. How you do that? So you take uh, your signature, and I will now explain. So you take your K that you generated somehow here, and so let me put it like this, -1. So, and this is, I will shortly tell you what it is. And you multiply your, it's really multiplication. So, oops, by h plus, um, so this r over here multiplied by this k prev. So the private number that you chose, and you do it mod n. Uh, this n is also part of the specification of the curve. So it's well, it has a meaning. So, but it is given to you. So it is part of the specification. So, but the point is that um, K and N, so they are relatively prime, and because N is prime, and K to the power of minus one. So this is the inverse of K um, mod N. So that's you can find using a Euclid algorithm or online calculator. Well, and I just want to say that you will I will not ask you to repeat this kind of computation. So, but what I just want to point out and is that calculation of the signature involves very simple operations. So this is similar to RSA. So you create a hash of the message. All others, so it's about simple multiplication of integers. And here, these transformations include not only multiplications, but still very simple. And finally, computing signature also involves very simple operations here. And now looking at my clocks, so I think we will end now. I will complement this notes with the verification part of the signature, so you can trace it at home. And also with the page showing why it works. But again, so that's only as an extra material. So in the case you're interested to understand that math actually works. What you have to remember are probably the very main basic principles of elliptic curve cryptography that I sketched here. So you need to know that all your computations are happening within the valid range defined by this equation over here, which is the definition of the elliptic curve. And because of this modulo, so all the computations are integers. Yes, and so we introduce a special operations, which are rather simple operations for transformation of points from one to another, so that we can hop from one point to another and cover the entire field, which is the range of values. Yes, and these operations are used for uh, digital signatures and even encryption. All right. Do you have any immediate questions? So let me see.
What do you think we should focus on until Friday? I remember last time before the quiz, you said that you wanted us to calculate, do the stuff on the paper. Do you have any
Yeah,
suggestions?
I do. I do. First of all, so be sure that you can trace computations of RSA. So that I mean, we covered yesterday, and I quickly reminded you today. And again, so know the fundamentals, so the basic principles of uh, elliptic curve cryptography. No computa. I will not ask for computations, but again, so the main principles uh, that I sketched here, and Diffie-Hellman. Again, also main principles. I will not ask you for calculations.
Okay, thank you.
More questions? Well, if not, good luck with the quiz. And next week it will be a practical session with the public key crypto. So that's it for today. See you.